The approximation method of Euler is again not a solving method for differential equations, but it is a method that could help us get a pretty accurate approximation for a single point on a solution function. If we are given a differential equation, and an initial value or a boundary value, so say x sub 0, y sub 0. So we need to know some point on the solution function. So that is, so what we're meaning by this is that phi of x is the solution of the differential equation. So at this point, we have no idea how to solve the differential equation and arrive at phi of x. But just theoretically, if phi of x is the solution function, what we're saying is that phi of x sub 0 equals y sub 0. Typically, how this is going to be given to us, though, is that it's going to be given to us as y of some value is equal to another value. But you'll see when we do an example. So with these approximation methods of Euler, and I know that doesn't look like Euler, so let me write that. It looks like Euler, maybe, but it's actually pronounced Euler. The approximation method for Euler, if we're given a differential equation and we're given a point that satisfies that differential equation, we could use that information to find an additional point that satisfies that differential equation. And again, we're going to be using the idea that this differential equation tells us tangent slopes. It tells us tangent slopes on our solution function. So what Euler tells us is, suppose this is our solution function. So we at this point have no way of figuring out what the equation for that function is. But if we know a function exists and we're given a point on that function, Euler says, find the tangent slope at that point. And we can do that because we have our differential equation. And our differential equation is can be used for tangent slope, as we saw in the last section. And I'm going to do that actually in a different color. So start at your point, find the tangent slope, and we're going to follow that tangent slope a little ways. So there's our tangent slope, and we're going to follow it a set distance, which we call our step size, and it's usually represented by h. This is the distance that we are going to follow each individual tangent slope. Now, as long as we don't follow it too far, we should be able to stay pretty close to the solution curve. So those step sizes usually are really small, like a tenth or 5/100ths. We try to keep them pretty small. So we follow it a certain ways, and then we stop, and we see where we're at. And then we reevaluate our tangent slope. We say, okay, now at this new spot, what is the tangent slope? Because this function is a curve, which means the slope is constantly changing. So I need my new tangent slope there. Sorry. I need a new tangent slope to follow. And once I have my new tangent slope, I'll follow it again for my step size. And it will take me to a certain spot. And then I will reevaluate my tangent slope again. And do your tangent slope, follow it your specified amount, take you to a new spot, and then reevaluate your tangent slope. Take you to a new spot, reevaluate your point, get a new tangent slope. Now, as long as we don't follow the tangent slope too far, as long as we keep this step size pretty small, these intermediate points that we're stopping at should still be really, really, really close to our phi of x. Now, they might not be exact values on the solution function, but they should be really, really close. So we want to keep this very small. So algebraically, what this looks like is we usually make a nice table to keep everything organized. Every single time we move, we're going to have a new x value and a new y value. So our step size is how much we're going to move in the x direction every single time. So if we start at x sub n, so that can represent any step along the way. The way that we get, let me go back, hold on. If we start at x sub n, the way that we get our next x value, x sub n plus 1, is we just add our step size. So from here to here to here, these are all evenly spaced. They're all h distance apart from each other. But the same might not be true for the y, because with the y, we're having to follow the function. But the x's are really easy. Every single time your x value is just increasing by h. Now for the y value, what we want to do is we've got to follow the slope. But we don't want to use the entire slope value, because remember, dy dx is slope. And if you remember from algebra class, that means the change in y over the change in x. And if you remember graphing lines in algebra class, if your slope ever ended up a whole number and you wanted to graph that line using the slope, we would always change it to a fraction. That way we could think of it as rise over run. Well, we're only running the amount of h every single time. We're only moving our step size every single time. So I don't want my run to be 1, I want my run to be h. So I could easily change that run to be h if I just multiply it by h, because right now it's 1. And in order to keep this value of my slope, of my fraction exactly the same, I just have to do the same thing to the top. And remember, this is change in y over change in x. So my x is changing by h every time. My y is going to change by slope times h. So my new y value is just my old y value plus slope times h. We're going to follow our slope, but we're only following it for a very tiny distance, and we're following it from the old y value to the new y value. And this is an iterative process, which means we're doing this over and over and over again, and once we get to a new point, we're going to redo this, and then that's now going to be our old point, and keep doing it over and over and over again. So that's why I said just a second ago, sometimes it's easier to keep track of all of the stuff we're doing if we create a table. So n is going to be the number of iterations. And then we're going to have an x, and we're going to have a y, and we're going to have dy dx. And then remember, h was our step size. And we're going to look at an example here. We're going to use the approximation method of Euler. To approximate y of 2 given dy dx equals x minus y, y of 1 equals 3, and h equals 0.1. So we were given a differential equation. At this point, we have no idea how to solve that differential equation. If we did, this would be a whole lot easier. So all we know is a differential equation. I know a point on my solution function. This represents the derivative of y, and remember, the solution to a differential equation is the original function. So notice there's no derivative here. This is now back to the original function y. So I know my differential equation, I know a point on the original function, and I want to use that information to figure out another point on the original function by doing step sizes of 1/10. So right now I have x equals 1, y equals 3, and I want to get to x equals 2 and figure out what y equals. So I'm going to have to take, to get from x equals 1 to x equals 2 with a step size of 1/10, I'm going to have to take 10 steps. When we set up our table, though, we typically start with n equals 0, because what they give us is x sub 0, y sub 0. So in my table, I've got n, x sub n, y sub n. And with that information, we can calculate dy dx. And then we can get x sub n plus 1. We can get the next x value and the next y value. So the first piece of information they give us is x sub 0 and y sub 0. So we've not done any iterations yet. They've given us that x is 1 and y is 3. So that is given to us. The way that we get the slope is right here. You do your x minus your y. So we're going to do 1 minus 3. We get negative 2. The next x value, remember our formulas are up here. The next x value, we're always just adding h to get to the next x value. And our h here is 1/10. So I started at 1 and I'm going up 1/10, so 1.1. The y value, though, is a little bit more involved. To get the new y value, we have to follow the slope. So we've got to use our old y value and follow the slope 1/10 of a unit. You do your slope times h, which is 1/10 right now. So we want to do our old y value plus our 1/10 of our slope, which would be 3 minus 2/10, which is 2.8. So this x and y value at the end of our row are going to slide down and become the new x and y point on the next row. So what we've done now is we have taken our initial point, we have followed the slope, and we've gotten to the new point. Now that we're at the new point, we need to calculate a new slope and follow it to another point. So now we're going to use these two values to calculate a new slope. Now the slope formula doesn't change. Slope is always x minus y. So now we're doing 1.1 minus 2.8, which is negative 1.7. Our next x value is really easy. We're always going up by a tenth, so it's 1.2. The y value, though, is a little bit trickier. We've got to do the old y value, which was 2.8. And then we're going to add the slope times the step size, which was a tenth. And at this point, we're going to start getting our calculator out. These decimals are going to start to get pretty long. So we've got 2.8 plus negative 1.7 times 0.1. And I've got 2.63. So we are not done until our x gets to 2, because we were asked to find y of 2. So we've got a lot to fill in here. This new x and y here are going to get transferred down. And we're on to the next iteration. Dy dx is x minus y, so 1.2 minus 2.63. I get negative 1.43. Your x is just a tenth bigger. And then your y, you're going to do your old y plus your slope times a tenth. So 2.63 plus negative 1.43 times a tenth. I get 2.487. Now don't round any of these numbers. We're going to try to keep all the decimals as we go. The new x and y get transferred down to the next. So 1.3, 2.487. dy dx, we're just referring back to the differential equation we were given, x minus y. So we're doing 1.3 minus 2.487. The calculations are really, really easy. It's just going through this whole process in this whole chart. We now have a slope of negative 1.187. The new x is just 1.4. So we're almost halfway there. And then we've got to do the y plus a tenth of the slope. So 2.487 plus a tenth of the slope. And I get 2.3683. And now these guys will get transferred down. And I'm just going to go ahead and pause the video and fill the rest of all of this in. And we need to get all the way down to, I'm going to fill the easy stuff in so you can see where we need to stop. We need to go until x sub n plus 1 says 2. So that is where we're going to stop, right there. So we need to figure out the y's, the dy dx's, and keep on going. So I've gone ahead and just finished filling in this table, doing the exact same thing that we did in the first 3 or 4 rows. Again, we were given the very first x value and y value, and we were given a formula on how to find dy dx. To find x sub n plus 1, we're just adding the h, but to find y sub n plus 1, we've got a formula. The y sub n plus 1, we said, is going to be y sub n plus dy dx times h. So I just used that all the way down. And then whatever you got for x sub n plus 1 and y sub n plus 1, we transferred to our next row to be our beginning x and y on the next row to continue down. And I just continued this all the way down until I had an x value of 2, because that is what we were asked to find back in the instructions. It said use the method of Euler to approximate y of 2. So when I finally got my x of 2, the y value that goes with it was 2.04603532. So we are going to say for our final answer that y of 2 is approximately 2.04603532. Now I did not do any rounding when I did this. I kept every single decimal that my calculator gave me. So if you do any rounding along the way, your decimals are going to come out slightly different. I just kept everything. So when I filled in the rest of the chart, this is what I got. And I just kept using the same formulas over and over and over again. The x's are really easy because for x we're just adding our h value every single time. But for y, we've got to do the old y plus the slope times h. The old y times plus the slope times h. That'll give us our new y. And like I said, as long as our step size is very, very small, on the graph you can see we only follow that tangent slope a short distance. We should stay really close to this graph. It shouldn't take us too far away from it. And then the final answer we get might not be exactly on the graph, but it should be really, really close. And we're able to do this without even knowing what the equation for that function is, without even knowing what our solution function is. We're able to get this just by knowing the differential equation and 1 point on the solution. Just 1 point to start with. And we're able to find a second point.